Hello everyone. Today we continue with the types of molecular velocities. Types of molecular velocities. Okay. So yesterday we have discussed that there are different types of velocities, right, ma'am? There are different types of velocities among the gas molecules. What are the different types of velocities? Most probable velocity. Most probable velocity. Next what? Average velocity and RMS velocity. RMS velocity stands for what? Root mean square velocity. Root mean square velocity is RMS velocity, right, ma'am? So yes, the three kinds of molecular speeds are related to each other as what? See, yesterday we discussed lastly this one. Most probable velocity means UMP. Most probable velocity. And average velocity is what now? UAV, average velocity. And URMS indicates what? Root mean square velocity. So most probable velocity, average velocity, RMS velocity. Three types will be there. So what is the formula for most probable velocity? Under root 2RT by M. Okay. And what is the formula for average velocity? Average velocity formula under root 8RT by pi M. And what is the formula for RMS velocity? Under root 3RT by M. So like this, there are three types of velocities. So the ratio of these three types of velocities can be taken as what? Under root 2 east under root 8 by pi east under root 3. So 8 by pi under root 8 by pi, how much approximately we take? Square root of 2.5 you can take it roughly. So here square root of 2, square root of 2.5, square root of 3. So that ratio of these three velocities will be 1 east 1.128 east 1.224. So what I told you to remember easily. So 1 east 1.1 east 1.2. So 1.2, 1.11 like this. So it is what now here U average, U most probable velocity. Most probable velocity, this is what now? U average and it is what? URMS. So this relation we can take here. So it is what now here? The ratio of three types of molecular velocities among the gas molecules. Is that clear, ma? So it's about what now here? The types of molecular speeds. Okay. So the next is that RMS speed at any temperature. RMS velocity generally we take here. In calculations and numerical problem, mostly which velocity will be taken? Gas molecule velocity means we take what? RMS velocity. Okay, RMS velocity or RMS speed at any temperature, at given temperature, may be related to its value at STP. Okay, at STP, RMS velocity is related to like this here. See here, now CT. CT means what now here at the given temperature? The RMS velocity at the given temperature. Here, sometimes I told yesterday, U otherwise C, anyone we can take for RMS velocity. RMS velocity we can use what? U otherwise C. So here C we have used here. So the RMS velocity at T temperature, at T degrees Celsius is equal to RMS velocity at 0 degrees Celsius. STP conditions meaning what? 0 degrees Celsius na? STP temperature how much? Standard temperature how much? 0 degrees Celsius. So at 0 degrees Celsius, RMS velocity into under root 273 plus T by 273. Okay, the relation between RMS velocity at T degrees Celsius and RMS velocity at 0 degrees Celsius is given by relation what? CT is equal to C naught times square root of 273 plus T by 273. So this 273 plus T degrees Celsius is nothing but what now? Capital T. Capital T means what now? Kelvin temperature. Kelvin temperature means what? Absolute temperature. So absolute temperature capital T is equal to what? Centigrade temperature plus 273. Small t degrees Celsius plus 273. So this relation we can use. Relation between CH T temperature and CH 0 degrees Celsius temperature. And C naught is what generally? RMS velocity at 0 degrees Celsius. RMS velocity at 0 degrees Celsius is equal to under root 3P by D. We know. So RMS velocity formula, three formula we have discussed now. So RMS velocity formula what? RMS velocity, URMS we can take, otherwise CRMS. Anyone is okay. So CRMS or URMS is equal formula what? Under root 3 RT by M, 3 RT by M, otherwise we take what? Under root 3 PV by M, 3 PV by M and 3 RT by M. These two kinds we can take, right now. So now here, in place of PV, what we can take? In place of PV, RT we can take here. So 3 PV or 3 RT we can take here. So in this case now, volume by mass is what now? Volume by mass is 1 by density. So here P is there here, P by D. So 3P by D. This one you can take. 3P by D. So C naught is nothing but RMS velocity at STP. STP means what? 0 degrees Celsius is equal to under root 3P by D. Okay, D is what? Density of the gas here. From equations 1 and 2, we get CT. CT means what now here? The RMS velocity at given temperature, T degrees Celsius, is equal to under root 3P by D. In place of C naught, what we have written? In place of C naught, what we have written? Under root 3P by D into square root of 273 plus small t by 273. So like this value, how much now? 273 plus small t is what? It is capital T. Capital T means what now here? It is absolute temperature. So absolute temperature by 273. Okay. So we get what now here? The CT value is equal to under root 3P of 273 plus T divided by 273D. So this will be what now here? The formula for calculation of URMS at given temperature T. At T degrees Celsius. At T degrees Celsius, the RMS velocity can be calculated by using this formula. Next. Now, very important points what we have to understand is that some essential points for distribution of molecular speeds. So distribution of molecular speeds. Different molecular speeds are distributed by whom? Maxwell and Boltzmann. So this is called Maxwell-Boltzmann distribution of molecular speeds. Right now. So in that cases, we have to remember some important points. First point what we have to understand is that the fraction of molecules. The fraction of molecules. So the fraction of molecules we write like this here. The fraction of molecules with very low, otherwise very high speeds. Okay. So what is the fraction of molecules having very low speed, otherwise very high speed is very small. See now, if you take for oxygen here, at one given temperature for oxygen gas we have taken. At a given temperature. At a given temperature for different gases. At a given temperature for what? For different gases we have taken here, this plot. So in this case, oxygen gas you take at the given temperature, oxygen curve is this for here. So in case of oxygen curve here, what we have to understand is that, see, now here, these many fraction of molecules have very less velocity. So it is very less magnitude of velocity. Here, very less fraction of molecules. Okay, man? So very low fraction of molecules, less fraction of molecules will have less velocity. And also you check it at the same graph, the same oxygen graph up to this here. Here at this point, the velocity, magnitude of velocity is very high. See, the velocity is very high here. So here also, this high velocity is also possessed by what? High velocity also is possessed by less number of molecules. So less fraction of molecules possess what? Very high magnitude of velocity. High magnitude of velocity. And very less number of fraction of molecules. Less fraction of molecules will possess what? Very low magnitude of velocity. So very low fraction of molecules, very less fraction of molecules will have the velocity, very low velocity or very high velocity. So very low velocity, very high velocity will be possessed by very less number of gas molecules. That point we have to understand. Next, maximum fraction of molecules have the speed near to the most probable velocity. To the most probable speed. Here VMP we can write, otherwise UMP we can write. V otherwise U, anyone we can use. So MP stands for a most probable. So most probable velocity, UMP or VMP we can take here. So now here, this is the highest point of the peak. So this highest point of the peak, this indicates which term, which magnitude here, RMS velocity or most probable velocity, which one it is? It is most probable speed. So it is most probable speed of what? Oxygen. Okay, from the height of this peak, we have to take the dotted line towards what? X-axis. Now this point will give what now? The value of most probable velocity of oxygen. So now see, this velocity is possessed by very large number of gas molecules here. That means a greater fraction of molecules. So more fraction of gas molecules will have most probable velocity. So what we have to understand is that the most probable velocity is the velocity or the speed which is possessed by a very large number of gas molecules at a given temperature. At a given temperature for given gas, the large number of molecules, more fraction of gas molecules will have most probable velocity. That point we have to understand here. Is that clear now? So this peak, height of the peak indicates which velocity here, most probable velocity here. What is the difference between what is important thing to remember about RMS velocity? Whose magnitude is greater? RMS velocity magnitude is greater, or most probable velocity magnitude is greater? RMS velocity magnitude is greater. The magnitude of RMS velocity is greater than average velocity, greater than most probable velocity. That point mainly you have to remember. Okay. So it's about the distribution of molecular speeds, first point. And second point, what we have to understand is that, so here, the second point is that, now second point, total area under the curve, okay, is a measure of total number of molecules. Total area under each curve is measure of what? Total number of molecules in the collection. Okay, thus area under the curve remains constant at different temperatures. At different temperatures, the area under each curve will be what now here same. Suppose you take here this one, at the given temperature, this is the area here. Okay, what is this one? So this is the area under this curve. Under this curve of oxygen, it is area. So this area is there here. Suppose this oxygen is taken at given temperature. At given temperature, this is the area under curve of oxygen. Okay, this area under curve of oxygen indicates what? The total number of molecules of oxygen. This area, total area under this curve of oxygen indicates what? The total number of gas molecules of oxygen. Okay, ma. Suppose if you heat the oxygen gas, what happens to temperature? The temperature of oxygen will increase. When you heat this oxygen, what happens? Its temperature will increase. Then what happens? This curve will flatten. The peak of this curve will become flat. Okay, the height also will decrease. The height of this curve, this oxygen curve height will be decreased. And also the peak becomes what? Now peak of the curve becomes what? Flat at high temperature. Like this, whenever this height decreases, when the curve height decreases also, the area under curve remains what? Constant. If you heat oxygen from less temperature to high temperature, okay, the total area under this curve will remain what? Same. Total area under the curve remaining same, meaning what? The total number of gas molecules will remain same, though you heat given gas from low temperature to high temperature. That point is mentioned here. Now, once again, see the second point. Total area under the curve is a measure of what? Total number of molecules. Total number of molecules in the collection. Thus, area under the curve remains constant at different temperatures. At different temperatures, the area under the curve will remain what? Constant. Is that clear, man? So that point mainly we have to understand here. Next. Now, distribution of molecular speed. So the distribution of molecular speed also depends on what now here? Depends upon molecular masses of the gases. Okay, molecular mass of the gas also will decide what? the distribution of molecular speed. So the distribution of molecular speed also depends upon what? The molecular mass of the gas. And at similar temperature means at same temperature, a heavier gas means gas with more molecular mass. A heavier gas molecule has a narrow distribution. Heavier gas molecule has what? Narrow distribution of speed than what? Those of lighter gas molecules. That means what now here? Suppose you take a curve of what now here? Oxygen like this. It is for oxygen. Now in this curve, what happened here? Narrow distribution is there here. Narrow. That means for the peak is the sharp. The sharp peak is there. Suppose if you take hydrogen gas like this, it will become like this for hydrogen. Hydrogen gram molecular mass is less. Now see the height of the peak became what now? The less, and also the peak became what? Very flat. The peak became what now here? Peak of the curve became what? Flat. And here narrow distribution for heavier gas and broader distribution for lighter gas. That means what we have to understand, if you are given suppose two plots like this here. Okay, two plots you are given like this here. So in this case, it is X gas, it is Y gas. X gas and Y gas given here. Now, which is having more molecular mass? If they ask you, what is having more molecular mass here? The X will have more molecular mass. Why? The narrow distribution is there for this curve of X. For the curve of X, narrow distribution of molecular speeds is there. That's why it will be what now here? It will be having more molecular mass. And this Y, gas Y, is having what? Broader distribution of molecular speeds. Okay, now which is having more height? Which peak is having more height? The X gas has more height and Y has less. Which one has more flat peak? More flattened peak is for what? Y here. So this point you have to understand. This X gas, Y gas, which one has more molecular mass now here? X has more molecular mass. X has what? Greater molecular mass. So molecular mass means molecular weight of this X will be greater than what? Greater than what? Y. So X has greater molecular mass than what now? Than Y. This point we have to understand here. So this is important question here. Next. The fraction of molecules having speeds. The fraction of molecules having speeds greater than minimum goes on increasing. The fraction of molecules having speeds greater than minimum goes on increasing with increase in what speed here. With increase in speed, what will be happening? The fraction of molecules will be increasing. So it reaches to a maximum value and then begins to decrease. So the same curve what we discussed is. So initially the curve will be going up like this. That means what? When molecular speed increases here. On the x-axis, what we take here? Molecular speed. On y-axis, what we take here? The fraction of molecules. The fraction of molecules on y-axis, the molecular speed on x-axis, right now. So when molecular speed is increasing like this on x-axis, what is happening to the fraction of molecules? Fraction of molecules increases and will reach maximum. After that, it will decrease like this. It will decrease. That means what now here, what they said, this point is see once again now. The fraction of molecules means this one. The fraction of molecules having speeds greater than minimum goes on increasing. So this point mainly remember here. The fraction of molecules, the fraction goes on increasing. The fraction of molecules goes on increasing like this, increasing with the speed. When molecular speed increases, the fraction of molecules increases. And this, it will reach what now? To a maximum value. It will reach a maximum value here. Maximum value. And then begins to decrease like this. So this is what now here, curve of distribution. Curve of what? Distribution of molecular speed. Next. Another point is that as long as temperature of the gas is constant. So when we keep the temperature of the gas constant, the fraction having a particular speed, remains the same in spite of what? The fact that the molecules change their speeds due to collisions. Okay, ma'am. So now here what they are saying is that when temperature is constant, the fraction of molecules remains constant. When temperature is kept constant, the fraction of molecules having particular speed will remain constant. But what will be changing when it is going on? The molecules are colliding with each other, and also molecules colliding with the walls of container. The collisions are continuing. But what happens? The fraction of molecules with particular speed will remain same when temperature is kept constant. Okay, I will send you this PPT once again. Each and every point go through thoroughly. Next, the increase in the temperature of the gas increases. The increase in the temperature of the gas increases the molecular speed. So the molecular speed depends on what? Temperature. See, any velocity you take here, suppose you take URMS formula what? Under root 3 RT by M. 3 RT by M, right, ma? So here RMS velocity and temperature, how these two related? Directly or inversely? Directly. So URMS is directly proportional to square root of what? Temperature. So when temperature increases, what happens? When temperature increases, RMS velocity also increases. Not only RMS velocity, any velocity, RMS velocity, average velocity, or most probable velocity. Any velocity will depend on what, ma? Will depend on this only, temperature directly. So temperature means what now here? Okay, so now RMS velocity is equal to under root 3 RT by M. Under root 3 RT by M, right, ma'am? So it's about the important point to understand here. So directly proportional, RMS velocity is directly proportional to square root of temperature. Okay, that's why when temperature increases, what happens? When temperature increases, automatically it will also increase here. Means velocity also will increase. So the same point you take it once again. The increase in the temperature of the gas increases the molecular speed. So as a result, the most probable speed increases. Most probable speed formula what? UMP formula what? Most probable speed under root 2 RT by M. So when temperature increases, what happens to this most probable velocity also? It also will increase. So like this, most probable velocity increases with increase in what? With increase of temperature. And the distribution curve shifts towards right. The distribution curve will shift towards right. Means at low temperature, the peak height of the peak will be more. At high temperature, the height of the peak will become less. We get another curve at high temperature. So the high temperature curve will have less height than what? Low temperature curve. That means what? The curve is shifting towards which side? Right side. So the general shape of the curve remains constant. When temperature is increased, the shape of curve, bell shape we say, whatever we discussed so far, the curves, which shaped curves? Bell, B-E-L-L, bell shaped curves. The shape remains same, but what happens? The height of the peak will decrease when temperature increases. Okay, that point you keep in mind. Now what happens here? But the shape remains constant here. But the maximum of the curve becomes what? Somewhat flat. The maximum means peak. The maximum meaning what? Peak. The peak of the curve becomes what? Somewhat flat. Means the height will decrease. So at a higher temperature, when temperature is increased, the peak of the curve becomes what more? Flat. That is, there is a wider distribution. The narrow distribution becomes what now? Wider distribution. At low temperature, narrow distribution. At high temperature, wider distribution of molecular speeds. And the fraction of molecules having high speeds increases. And the fraction of molecules having high speeds will increase. Okay. So, however, the fraction of molecules possessing most probable speed decreases with increase in what? Temperature. So what we have to understand is that the fraction of molecules possessing most probable speed decreases with increase in temperature. Okay, so only one point you have to understand it. Suppose we have taken one curve like this. Here fraction of molecules versus what? Molecular speeds. Fraction of molecules versus molecular speeds. Here, at low temperature, we got like this. It is the curve. It is at T1 temperature. This T1 temperature is low temperature. Take it like this. Now, narrow distribution is there now. Narrow distribution. At this T1 temperature, it is what now here most probable velocity. It is what now most probable velocity possessed by these many molecules. Okay. Now, what I am taking here, it is increased to T2 temperature. Now here T2 is greater than what? T2 is greater than T1. That means when temperature is increased from T1 to T2, what happened to the curve? You see, the curve became what? Flat. That means for the peak, the maxima of the curve became flat. Right? That means what now here? Here the most probable velocity is possessed by less number of molecules. So this peak, height of the peak indicates what? Most probable velocity, right? It is most probable velocity. So this most probable velocity at this T2 temperature, at the T2 temperature, most probable velocity will be possessed by less number of molecules. At T1 temperature, this fraction of molecules having what? Most probable. But at high temperature T2, less number of molecules have what? Most probable velocity. That's what it is given here. See. However, the fraction of molecules possessing means having. The fraction of molecules having most probable speed decreases with increase in what? Temperature. When temperature increases, the fraction of molecules with most probable velocity will decrease. So this point keep in mind. So now what we understand, when you are given T1 temperature, T2 temperature, which is greater than which one? Which temperature is greater than which one? If they ask you, how to say? The narrow distribution of curve. Narrow distribution of curve at low temperature. Narrow distribution of curve at low temperature. And broader distribution of curve. Broader distribution of curve. Wider distribution of curve for high temperature. This point keep in mind. And already we discussed about what now here? The heavier gas and lighter gas, na? The same thing, fraction of molecules versus what? Molecular speed. Fraction of molecules versus molecular speeds. If you take now, we discussed earlier, it is what now here? O2 for oxygen. For oxygen, it is curve, and it is what now here for hydrogen. Suppose. Okay, that means between these two, which is lighter gas? Hydrogen is lighter gas. So oxygen is heavier gas. For heavier gas, what is to be understood here? The narrow distribution of molecular speeds. That means the peak of the curve is sharp. And for lighter gas like hydrogen, here the peak of the curve will be less height. And also the peak is flattened. The flat peak, the maximum becomes what? Flat here. And also the what here? This lighter gas has what now here? Less what here? Fraction of molecules with the most probable velocity. Okay, man? So this point, these all points will depend on what no formula only. Simply, see, in this case, what is the formula for you most probably? Just tell me. Okay, in this case now here, what is the formula for most probable velocity? UMP formula, tell me. Most probable velocity is equal to under root what? 2RT, under root 2RT by M. Na? So under root 2RT by M. So in this case, now how molecular mass of the gas and most probable velocity related here? Most probable velocity and molecular mass, these two are inversely proportional. Na? Inversely proportional meaning what? Inversely proportional means what down here? Whenever molecular mass is more, the UMP will be less. When molecular mass is more, UMP should be less. Now see here, oxygen has molecular mass 32 grams and hydrogen gram molecular weight is 2 grams. Now more molecular mass is for oxygen, that's why the most probable velocity will be less. Most probable velocity will be less. But for oxygen, for hydrogen, the molecular mass is less. When molecular mass is less, this most probable velocity will be high. That's why it will be very high. Okay, ma'am. So it's about what now we have to say here. So like this we can take here concept. So if the narrow distribution of curve is there, the most probable velocity magnitude will be less. Most probable velocity is less, meaning what? The molecular mass should be high. That's why oxygen is having more molecular mass. Next one here, for in case of hydrogen gas, which is lighter gas than hydroxygen. In this case, what we have to understand. So this from the peak, from the height of the peak, we take what now here? From maximum we take a line towards x-axis. This value will be giving what now here? Most probable velocity of what? Hydrogen. Most probable velocity of our hydrogen gas. It is what now? This is what? Most probable velocity of oxygen gas. Now, which one has more magnitude of most probable velocity? Hydrogen has more magnitude of most probable velocity. Why? Why? Because the hydrogen has less molecular mass. Therefore, most probable velocity will be high. Are you getting one? And now in case of O2 gas and H2 gas, in case of heavier gas and lighter gas, in which case, more fraction of molecules having most probable. Here, in case of oxygen, more fraction of molecules have most probable. In case of hydrogen, less number of fraction, means less fraction of molecules have what? Most probable velocity. So these points we have to understand. So it's about what now here important areas to understand here. These two plots are important here. It is what now the plot of what now here two different temperatures. Now for same gas, but this plot is what now here for same gas but different temperatures. It is for same gas but at different temperatures. Now we have two different gases at same temperature. Two different gases at same temperature. So temperature is same here in this graph. Here in these plots, temperature is same for different gases. But here the temperature is different but same gas. Okay, so these two curves are only very important here to understand in this. Okay, ma. So next one, what we have another one, same example what we discussed only. So fraction of molecules means how to write now? Fraction of molecules versus molecular speed. Okay, so if you take this one on y-axis and it is on x-axis, what we have to understand here at T1 temperature. Here already given what now here T2 is greater than T1 means what now here T2 is high temperature, T1 is low temperature. So at low temperature the distribution of molecular speeds is narrow. So what we have to say here? So it is low temperature, right? At low temperature, a narrow distribution. What we have to understand here? Narrow distribution of molecular speeds. At what temperature? Low temperature. Whenever narrow distribution curve means what here? The height of this peak will be more. Height of the peak is more, and more fraction of molecules will be having most probable velocity. And narrow peak means what? Now peak is very sharp. It's not wider. Sharp peak will be there. Means the narrow distribution is there here. Right, ma'am? So it is the T1 temperature. Now, when you increase the temperature of the given gas from T1 to T2, now this is for same gas, now let it be nitrogen gas. For nitrogen gas, I'm taking suppose here. For the same gas at two different temperatures, I'm taking. So this is the curve of nitrogen at low temperature. This is the curve of same nitrogen at high temperature. So when temperature is high, what we have to understand here? A narrow distribution or wider distribution here. So we have to understand wider distribution of what? Curve. Wider distribution of molecular speeds at high temperature. Now this is the total area under what? Curve of T1 temperature. This is the total area under curve. Okay. Now the total area under curve of T1 temperature and the total area under the curve of T2 temperature, both will be same. Remember, the area under each curve, the area under T1 curve, the area under the total area under T2 curve, both will remain same. When we increase temperature, there is no change in the total area under the curve. The total area under the each curve indicating what? Number of molecules. Now at low temperature, X number of gas molecules of nitrogen. At high temperature also, same X number of gas molecules only will remain. Number of molecules will not change when we increase temperature. That is why the total area under each curve remains constant, means what? The total number of gas molecules at two different temperatures will be remaining same. That point mainly you have to understand here. So it's about what now here? The concept of molecular speeds. Still it is to be discussed. Okay. Bye. Good day. Take care.